Okay, there we go. So remember, and then we kind of built up to this idea of what if it's not a nice shape? And what if we still want to try to estimate the area underneath of that function, but we don't know the shape of that function and the area to actually estimate that shape? We're going to use kind of our known areas by just essentially breaking that up into a bunch of rectangles. Just in case I forget to say it and you see this word somewhere, these are called Riemann sums. And I can't remember if the E comes first or the I comes first. It's a guy's name. I'm pretty sure it's spelled like that. But they're called Riemann sums. So if you ever hear me say Riemann sums or you see Riemann sums somewhere in Wiley or something like that, this is what it's talking about. It's talking about these kind of rectangle estimation things. So to remind us what we're doing before we do one of our first official examples is we're essentially taking this function over whatever, interval we're looking over. We're breaking it into a bunch of rectangles. And remember, we're essentially having two choices for the heights that we're going to let the rectangles be. So we're going to break it up into kind of these equal pieces. And so all of the widths of the rectangles are going to end up being the same. But the lengths of the rectangles, the heights, if you want, are going to kind of depend on whether or not we take the y value from the right side or the left side of the interval that we're working over. So we'll have things called right-hand sums and things called left-hand sums. So say we want to do this first example down here. So suppose a car is moving with increasing velocity and that we measure the car's velocity every 2 seconds, obtaining the data given in the table, estimate the distance traveled in that 10 seconds. Now, a couple things. In terms of these questions, sometimes they tell us how to break it up and sometimes they don't. So in this one, this is an example of them not really telling us explicitly how to break it up. But since they give us a table, what we're going to do is we're going to break it up into as many pieces as we can. So we're going to break this up every 2. We're essentially going to take 0 to 2, then 2 to 4, then 4 to 6, then 6 to 8, then 8 to 10. So since they kind of break it up in that way for us in the table, we're going to take essentially as many intervals as we can. Again, sometimes they will specify how many they want you to break it into, and we'll see that. I think we'll get to an example that does that, but that'll be towards the end of class. But anyway, now you don't always have to draw the situation out, but to kind of make sure we kind of know what's going on here, I'm going to go ahead and draw out the function for this one. So you've got 2, 4, 6, 8, 10. Again, this is not a necessary step, but I think it'll help demonstrate what we're doing since we're still just kind of learning it. Here we go. So we have, what do we have? We have 0, 20. We have 230. We have 438. And then 644, 48, and 50. So not exactly a scale. I think they started to get a little too large there. I think my 50 is a bit off. Now let me just move that up and make that a bit more. There we go. Fixed it. So our graph looks something like that. And also my 10's a bit off then too. So let's just move that too. There we go. So we're breaking it off at 10. So again, if we kind of look at it in terms of the graph, again, you don't need the graph here. You don't need to draw the graph for these tables. You can just do the problem based off of the table. But if I draw this, notice that that's a shape that I don't know the area of. It's not a rectangle. It's not quite a quarter of a circle. It's not a trapezoid. It's not a triangle. I don't know the area of that. So we're going to have to estimate it using this idea of this right hand and the left hand sum. Now in this case, again, they don't really specify what one they want us to find. Specifically in this one, we're going to find both. So we're going to find the right hand side and the left hand side sum. If they don't specify, you usually only have to find one of them. So if they don't specify, you kind of get to choose. But since, again, this is our first example, let's go ahead and find both of them. So I'm gonna, well, let me match. So yeah, my right side was in blue. My left side was in green. So we're going to find the right-hand sum, which I'm going to start abbreviating RHS, and then the left-hand sum, which I'm going to start abbreviating LHS for these. So one thing Let me move this down a little bit so I can write something else. One thing that you don't have to do, but I think a lot of people sometimes tend to like to do is think about what we're splitting this up into. So if we kind of split this into a bunch of rectangles, a rectangle between 0 and 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10, we're essentially on these intervals, 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. And I think writing it out in intervals like that is going to make seeing the right hand versus left hand easier. Again, not a necessary step, but if it helps you, totally do it. So say we want to do the right hand sum first. So essentially, if we were to draw that on this graph, we have these, we're essentially breaking this up into 5 rectangles. 1 there, 2, 3, 4, and 5 rectangles. So if I want to do a right hand sum, I have a rectangle in this first piece, but I'm essentially using this right end point at x equals 2. I guess t equals 2 in this case. And I'm using that y value as my height. So I'm going up to the right endpoint and using that as my height. And then for the second rectangle, I'm going to the right side, which would be t equals 4, using that for my height. For the third rectangle, I'm going over to 6 because that's kind of my right side of my interval there. For the fourth rectangle, I'm going over to 8. For the fifth rectangle, I'm going over to 10. So if you kind of write it down in these interval ways over kind of below the table like I did. So the right-hand side, we're going to use 2, 4, 6, 8, and 10. It's the right side of all of those all of those intervals. So the first interval is from 0 to 2, so we're going to use 2. We'll have the y value at 2. Second interval is 2 to 4, so we're going to use the right side, so the y value at 4, and so on and so forth. So we're trying to estimate an area here, so that means we're going to take all of the areas of the rectangles and we're going to add them together. So if we consider rectangle 1 that has a width of 2, since it's going between 0 and 2, and the height we're choosing is the height at x equals 2, t equals 2, sorry. So the height at t equals 2 is 30 from our table. So that'll be the area of the first rectangle. Sorry, I gotta remember to breathe every once in a while and slow down. Y'all can always tell me to slow down if I start going too fast. And then our second rectangle has a width of 2. Since it's between 2 and 4, the y value we're going to use is at 4, so that'll be 38. The third rectangle has a width of 2. And since it's from 4 to 6, we're going to use the y value at 6, so 44. Fourth rectangle, and then we'll need the fifth rectangle. So those both still have a width of 2. The width is going to be the same for all of our rectangles. So the fourth rectangle goes between 6 and 8, so we're going to use the y value at 8, the right endpoint, so we're going to have 48. And then the right endpoint of the last interval is 10, so we're going to use 50. If you punch all that into a calculator, you will get 420 feet. Since this is in feet per second, it'll become feet. Any questions on how I got any of those pieces or got any of those numbers or how I put it together or anything like that? Give anybody a couple of seconds in case they're typing it out. Okay. Okay. Actually, I want to move this down too because I'm going to want to write something else in a second. Slow it down a little bit more. So then if we use the left-hand side, we're still breaking it up into these 5 rectangles, but now the heights are going to change, the lengths, whatever you prefer to call it. So instead of using the ones at 2, 4, 6, 8, and 10, we're going to use the left endpoints of all of these intervals, so 0, 2, 4, 6, and 8. So if I were to draw that on my graph, I'd be using the left side for the height of the rectangle, and then the left endpoint for the height of the rectangle, and then so on and so forth, left side of the interval, left side, left side. So I know they overlap a little bit, but. So if I were to write this one out first rectangle, all of them have a width of 2. So let me just set that up really quick. So all of these have a width of 2. And on the next one, I'm going to write it in a slightly different way, so you don't have to write it out like that every single time, but just try to be super clear where all these things are coming from. On this one, I want to be kind of super generic. So the first rectangle is between 0 and 2. So if we're using a left-hand sum, we're using the y value at 0, so 20. And then the second rectangle between 2 and 4. So if we're using a left-hand sum, we're using t equals 2 for the y value, so we're using 30. And then we're using the y value at 4. 38, and then the y value at 6, 44, and then the y value at 8, so 48. I'm recording, right? Yes, I am. Okay. Punch that into a calculator, you'll get 360 feet. Any questions on how I got that? Okay. Now, what's the point of finding both of them? Again, you'll usually only be asked to find one or the other. In this case, it's not too terrible to ask you to find both, but in some of them, when you start getting more rectangles or smaller rectangles, and there gets to be more terms, then it can be super tedious to find both of them. But essentially, it's just a way to be able to find two different estimates, because notice that they're pretty far off from each other if you think about it. So I know that somewhere between 360 and 400 is my actual area, but I'm not exactly sure where. But that at least gives me a not huge interval to work over. Also notice that in this specific case, that the right-hand side, all of the rectangles ended up being above the function. That last one, you know, is kind of pretty close, but especially the one in the front, all of them end up kind of above the function. So this right-hand side is going to end up being what we call an overestimate, and we're going to talk about more about that in a second. And notice that the ones that I drew in green, or the left-hand side, scroll down. All of the rectangles end up pretty much below the actual function, so we don't get enough area. So that's going to be what we consider an underestimate. So that's not always going to be the case. Okay, so I don't want you to associate left hand with underestimate and right hand with overestimate. But in this specific case, that's how it worked out. So, still not seeing any questions, but feel free to stop me if you have any. So in some situations, but not all, we can look for these overestimates, so overestimation, or an underestimation. Which will provide either a too large or a too small estimate, respectively. Now, a function has to be purely increasing or purely decreasing on an interval to be able to classify it as an overestimation or an underestimation, and I'll show why in a second. But essentially, we kind of have four options if it's purely increasing or purely decreasing. So four options here. And I'm going to make two of these increasing and two of these decreasing. They don't have to look exactly like this, but just something that's increasing and then something that's decreasing. So, well, hold on a couple seconds in case people are catching up. So let me look at a right-hand side sum for those first two and then a left-hand sum for those last two. So if we do a right-hand sum on both of these, so let me say I break it up into like 4 pieces. So right-hand sum, go up to the function at the right side of the interval. Not the prettiest looking thing ever, but good enough to demonstrate what I'm trying to say. right side, right side. And then this one kind of just falls directly flat on the x-axis. So notice when we're increasing, when we have an increasing function, the right-hand side is going to end up being an overestimate. But once your function changes to decreasing, the right-hand sum now becomes an underestimate. Which is why I was saying don't associate right with over and left with under. It depends on whether you're increasing or decreasing. And then if we do left-hand sums, 1, 2, 3, 4, 1, 2, 3, 4. So go up to the left side, left, left, and then left, left. Ooh, these do not look pretty. So essentially, when you do the same thing for an increasing and then decreasing function, but in a left-hand sum, it kind of switches. So, oops, I forgot to put left-hand sum under both of these. Left-hand sum, left-hand sum. So for an increasing function, the left-hand sum turns out to be an underestimate. And the decreasing turns into an overestimate. Now, I've got to babble a little bit. Wiley and your book really likes to classify things as overestimates or underestimates, which is, you know, fine and dandy until you get something that can't be classified as an over or an underestimate. So for them, and for your homework that'll be coming up next week, sometimes they'll say find an underestimate, and you'll have to figure out whether the function's increasing or decreasing, so are the values increasing or the values decreasing. And then figure out whether the overestimate is a right hand or a left hand, depending on that. If I write a question, so quizzes, exams, all that jazz, if I write a question, I always do it in terms of right-hand sum and left-hand sum. I never ask you to find an overestimation or find an underestimation. Now, sometimes I'll ask you to classify it as an underestimate or an overestimate, if it can be one of the two. So you'd have to be able to like look at a graph with the rectangles drawn on it and figure out if it's an overestimate or an underestimate. But I will never say, here's a table, find an underestimate. I would say, here's a table, find a right-hand sum. So Wiley can get a little iffy because you kind of have to think about it a bit more. I think it makes more sense to do right-hand versus left-hand, but just know that they do underestimates and overestimates for some of their questions, and we'll see that in a second. One of the questions we'll get to today is a question from your book, and it does say find an underestimate. Then we have to think about it and figure out what type that is. But anyway, I'm going to squeeze down here at the bottom an example of why we don't always have these classifications. So say I have a function that looks like this. That's a little too steep. Let's not make it get all the way down to the, there we go. And let's say I want to take a right-hand sum here. So I don't know, just break it up into a couple pieces. So if I do a right-hand sum for this, okay. So notice if I do a right-hand sum for this, and it would be a similar situation if I did a left-hand sum, there's some rectangles that are overestimating and some that are underestimating. And then there's this one in the middle that does like a little tiny bit of both. There's like this tiny little sliver that's above and then a bit that's under. So if the function isn't purely increasing or purely decreasing, we can't say whether it's an underestimate or an overestimate, which is again another reason why I always classify them with right versus left, because sometimes the overestimate versus underestimate doesn't exist. But anyway, so sometimes you can't classify a sum as an under or an overestimate. If it's a purely increasing or purely decreasing function, you can, but once you get increasing and decreasing pieces, things fly out the window because we don't know if like the overestimation pieces are more or less than the underestimation pieces, unless I were to know the actual value and then I could compare. But anyway, Hopefully that makes sense. So overestimation, underestimation are decent classifications, but I will usually classify things as right versus left-hand side sums if I'm asking you to find them. If I want you to look at a picture and classify it as an increase, as a over or underestimate, I do ask those types of questions. Anyway, so let's do another one. Now, up to this point, we've been working with velocity functions, and that last one was a velocity table. It doesn't have to be velocity. Like, it doesn't have to be velocity for us to be able to do these Riemann sums. We can do them for kind of anything. Usually the thing we're going to be given is we're going to be given a rate, and we want to find the area underneath of that rate function. So here, the function we're given in this table is the rate of sales. So we're looking at a rate of sales of a new video game shown in the following table. Assume that the rate in sales increased through the 20-week period. Estimate the total number of games sold during this period. Now, again, they don't really tell us how to set up the rectangles. They don't tell us how many to use. They don't tell us the widths they want us to use. So we kind of get to choose. And again, when you're given a table, you kind of want to choose as many rectangles as you can form. So we're going to kind of use all those intervals, if you will, 0 to 5, 5 to 10, 10 to 15, 15 to 20. And again, they don't specify right versus left or even under versus over. But since we're doing this as just a pure example, we're going to do both. Usually you would just have to find one, but we're going to do both for the sake of making sure we're understanding these. So I'm going to write down the intervals we're working over again in case anybody likes that being written out like this. So we're over 5 to 10, 0 to 5, 5 to 10, 10 to 15, and 15 to 20. So now nope, I don't need to say that at all. I'm not going to draw the picture for this one because, again, as I said last time, it's not something you need to do. So we're just going to go ahead and jump straight into doing the right-hand side and the left-hand side. Oh, I need to talk about this too. In terms of your Wiley homework for next week, so the stuff that's up right now is on chapter 4, so it doesn't matter for this one, but on the next homework that you're going to have, it's going to be on this type of stuff. So you're going to see stuff like what is n, what is delta t, or delta x, whatever variable you're working over. And so if you see n, that's going to mean the number of rectangles. Oh, I should also say sometimes they're called subintervals. I didn't tell that to my last class, I forgot. So sometimes they might say break it up into 5 subintervals. That means break it up into 5 rectangles. And the delta t or delta x or delta whatever variable you're working with, that's going to be the width of the rectangle. And specifically for the ones we're doing, we're taking all of the widths to be the same. So in this case, for this example, since we have essentially 4 of those subintervals that I wrote down, so that's why they're also called subintervals. It's the 0 to 5, 5 to 10, so on and so forth. So we have 4 subintervals, so there's 4 rectangles, so n would be 4, and delta t would be 5, because each of the intervals goes, has a width of 5. The difference between the first endpoint and the last endpoint is 5. So just in case you see those on your homework for next week, those are what those mean. Now, for the sake of our, sanity in handwriting, let me scroll up really quick. Notice when we were doing this before, since we're taking the widths to be the same thing, in the first one we did, it was 2 times this and 2 times this and 2 times this and 2 times this, and we wrote 2 times something a bunch of times. Since the width is going to be the same in all of those rectangles, you could kind of factor it out of all of those pieces and just put it in the front. So that's what I'm going to do for this one. If you like to write them out fully, go right ahead. But I start to get really lazy. So since all of these rectangles are going to have a width of 5, I'm going to go ahead and start this, right-hand sum with just a 5, and then I'm just going to write all the lengths in here, or the heights, whichever you prefer to call them. So if I'm using a right-hand side sum, so my first interval is from 0 to 5, so I'm going to use 5, 10, 15, and 20. So we'll be using the 585, 892, 1875, and 2350. And so those will be all of our heights of our rectangle. So they'll go inside of my brackets. You don't have to make them brackets. They can be parentheses, but I just like using brackets. So essentially, if I were to distribute this out, that would give me the 5 times 585, 5 times 892, 5 times 1875, 5 times 2350. So putting it in the front, that 5, that width of the rectangles is just a way to make you write less things. If we were to punch that into a calculator, because I hopefully trust and believe we can do that, you will get 28,510, and the units here are going to be games. So essentially, the units for these, you're always going to be given a, well, 95% of the time, you're going to be given a rate. So the rate we were given was games per week. So whatever the rate is, the units of the sums are essentially like the numerator, if you will. So when we were doing velocities, they changed from like miles per hour to miles, or feet per second to feet. So since this is games per week, the result is going to end up just being an amount of games. So that would be our right-hand sum. And then our left-hand sum. We're now using the values at 0, 5, 10, and 15. The left side of the endpoint, the left endpoint of the interval. So the width is still 5, and again, to save myself some writing, I'm just going to write the 5 on the outside. So we're using the values at 0, 5, 10, and 15, so we're essentially using these first 4 and just leaving out the 2350. So we'll have 0 plus 585 plus 892 plus 1875. Punch that into a calculator, you get 16,760 games. Questions, concerns on how I found any of that? I'll wait a couple seconds just in case. And also let people catch up, because I've been forgetting to do that. Okay. Now, in general, so now we know that, since this was an increasing function too, because we're told to assume the rate of sales increased, since this is an increasing function, that right hand is going to be an over and the left hand is going to be an underestimation. So we know that the actual number is somewhere between those two. What if we wanted to try to get a slightly better estimate? So a slightly better estimate, and if you're not asked, so if it doesn't specify a right versus left in Wiley, this is usually the number they're going to try to go for, I believe. I'll triple check that before I assign the homework and tell you on Monday. But I think they usually want you to do this. And again, I'll triple check and tell you on Monday. But another way we can get a better estimate here is to essentially average those two. So average the two, right versus left. So if we take those two kind of sided sums, if you will, and we average the two, so add them both together, divide by 2, you get 22,635 games. And this would be kind of the best estimate we can do with the information we're given. We find the right and the left and then average the two. Now, someone in my last class asked, how do you know what answer I'm looking for, say on a quiz or exam? I am very specific in what I ask you to find. I either say find a right-hand sum, find a left-hand sum, or sometimes I'll say find the best estimate you can, and by best estimate, I mean find them both and average them. So I try to be very specific with my wording, right hand, left hand, best estimate, to make sure that you know what I'm asking you to find. Now, if I don't specify, if for some reason it doesn't say right hand, left hand, or best estimate, it just says estimate. It doesn't say best estimate, it just says estimate. Then you get to choose, because if I don't specify, that's my fault. So if it doesn't specify, you get to choose. But usually, if I have written the question, it will usually specify what I want you to find. I'll hold on like 5 more seconds before I go into the next one in case anyone has questions. Okay. Okay. So the next one is the last one in 5.1, and it's slightly different because it's not a table. So now we don't have a table. So we have if T is in hours since the start of a 20-hour period, bacteria population increases at a rate given by 3 plus 0.1 T squared. Make an underestimate for the total change in the number of bacteria over this period using, and we're going to use a couple things. So this is where that delta notation kind of comes in. So we're being told delta T is 4, and then we're going to do it again with delta T is 2. And then I actually meant to remove this one because that one gets a little too tedious. So we're just going to talk about this one. And I don't know if we'll get to it today. We have more time than I did in my last class, but if so, we might get to it today. But anyway, so we're just going to talk about that one and not actually find it because that one gets a bit tedious. Like the first two weren't tedious enough. Anyway, so this delta, remember, that's essentially the width of the rectangles. So we're told that we're going over a 20-hour period. So let's figure out how many rectangles that would mean for parts 1, 2. Well, let's do parts 1, 2, and 3, even though we're not going to do 3 out fully. So if we're going over a 20-hour period, so essentially between 0 and 20, because it says since the start of a 20-hour period, so 0 to 20, if the width of the rectangles is going to be 4, and we're going over 20 hours, that means we're going to end up with 5 rectangles. So essentially n equals 5. So there's going to be 5 rectangles in the first case. Essentially 20 divided by 4. What's your total length of the interval divided by what the width of the rectangles are? So 20 divided by 4 gives us that we're going to have 5 rectangles there. And then if we change it to delta T being 2, well, now we're going between every 2. So that's going to give us 10 rectangles. And the reason we're not going to do number 3 is because that would be 20 rectangles, and that's just too many. I usually never ask you to do more than 10, and asking you to do 10 is actually quite large for something that I would write. So that's why we're just going to talk about number 3 instead of finding it for 20 intervals. That's just obnoxious. But we will do the 5 and the 10. So we weren't given a table here, but we can totally go and find one. And I think it's helpful for the next step of the problem. So I'm going to go ahead and do so. So I'm going to find a table of all of our values. But what values do I want to use? Do I need to find all of them between 0 and 20? Not quite. So if we think about the first one, where we're doing delta T equals 4, essentially we're going to need 0, 4, 8, 12, 16, and 20. We're going to need every, fourth term, if you will. So for that, we would need, now I'm going to leave space strategically, 8, 12, 16, and 20. So we're going to need all of those values for the first one. But then for the second one, since we're going delta T equals 2, we're going to need our intervals to be something like 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, and so on. So we're also going to need 2, 6, 10, 14, 18, which is why I strategically left space there. So we're going to need all of these values eventually. And this is, again, why we're not doing number 3, because if we were doing number 3, we would also need 1, 3, 5, 7, 9, blah, 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 blah. So let's just not do that one. Now, this would be a really great chance to use that table function on your calculator if you have the TI-84 or 83. Type in that function 3 plus 0.1 t squared and then use the table to find all of these instead of having to punch it in 10 times. For the sake of time, I'm going to hopefully trust and believe that we could find all of these values, and I'm just going to tell us what they are. So if we plug in 0, we're going to get 3. And then 3.4. And then 4.6. And then 6.6. 9.4. 13. 17.4. 22.6. 28.6. 35.4. and then 43. So we'll need all of those values eventually. We don't need all of them for the first one, but we will need all of them for the second one. Well, kind of, not really. We're gonna, anyway. So that's another thing with the table examples. If you're given a table and they specify how to find how to split up into a certain amount of rectangles, you don't always need all of the values on the table. So be really careful with the table ones, read them and see if they tell you how they want to break it up. Because if they tell you how to break it up and then you don't have to use all the values, but you do anyway, then you're wrong. So one other thing we have to kind of clarify first before we move on to actually calculating this is, again, because this is a question from your book, it says underestimate. Now we're also told that this is increasing. So if we have an increasing function and we want an underestimate, if we kind of go back to those drawings I did beforehand, and literally, since you'll only have this type of clarification on your homework and Wiley, you can literally just pull them up. So we have an increasing function and an underestimate. That's essentially going to be this third one. So we're going to look for a left-hand sum. So since they want an underestimate of an increasing function, we're going to need a left-hand side sum. Again, if I write the questions, I will always say left side, right side, not underestimate versus overestimate. So we should have enough time to do both of these, so that's cool. And yes, writing these out do get a little bit tedious, but it's what we've got at this point. So the first one, I want to break down just the slightest bit more before we write it out to remind us that here, since we're going on delta 4, we're going from 0 to 4, 4 to 8, 8 to 12, also in case anyone really likes this interval notation, and 16 to 20. So we're using a left-hand side sum, so we're going to need the values at 0, 4, 8, 12, and 16. So here's a case where, like, if I was originally given this table, but then asked to let delta t be 4, and I used all of the values, I would have been wrong. So don't always immediately jump to, oh, I see a table, I use all of them. Triple check the question and make sure they don't specifically specify. Anyway, so the widths of all these rectangles are 4. So I'm going to go ahead and put 4, and then I'm just going to write all the lengths, the heights, whichever you prefer, in the middle. So what's our height for our first interval where we're working with the y value at 0, so 3. And then the y value at 4, so 4.6. So just trying to be super clear. Y value at 8, 9.4. Y value at 12, 17.4. And y value at 16, 28.6. So we broke it up into its intervals in terms of lengths of 4, widths of 4. I should be careful with that. Widths of 4. And then we took the left-hand side for our y values, punched that into a calculator. You'll get 252. I'll wait a couple seconds in case there are questions on that one before we'll do part 2. Okay. Now part 2 is going to be a lot of writing because we have to use 10 terms, which is again why the largest one I will ever ask you to do is with 10 terms. I will personally ask you to do. I don't know how crazy Wiley's going to get. But so our width here is now 2. So if you wanted to do your intervals, you would write 0 to 2, 2 to 4, and I'm going to be lazy, and you'd have to go all the way up 16 to 18, 18 to 20. So if you really like writing those out, and if you'd have to write all of them out, then you'd have to write them all out. But our widths are now 2. We're still finding a left-hand side sum here, so we're going to use essentially 0 up to 18, because 18 is going to be the last left side endpoint of our intervals that we're working over. So if our widths are 2, we just then have to add all of the lengths together. So yes, there are a lot of them. So we've got 3, 3.4, 4.6, 6.6, 9.4, 13, 17.4, 22.6, 28.6, 35.4. So those would have been all of the y values associated with one of the left endpoints of my intervals that I'm working over. Punch that sucker into a calculator, you'll get 288. So notice the difference between those two answers. We've gotten a larger answer, but since it's an underestimate, that kind of makes sense that the underestimate should be getting larger because we should be getting closer to the actual area. And since it's an underestimate, we should be going up. Now, if we were to take the time to find all of the numbers between 0 and 20 and add them all up and multiply them all by 1, because that would be the width. If we were to do that, with delta t equals 1, the value you would get for the left-hand side would be 307. So again, we're increasing a little bit. Now, if you're curious, the actual area is, and maybe you're not curious, but in case you're curious, the actual area is 326.67 approximately. So notice that the first estimate we had 252 was actually pretty far off the actual area, and we were getting closer and closer the larger amount of rectangles we were using, which is kind of the point in what we're going to talk about in 4.2 on Monday. So it's better the more rectangles you use, but of course, the more rectangles you use, the more obnoxious the problem becomes. But essentially, if we could end up using kind of an obnoxious amount of rectangles, if it would make sense if we could use infinitely many rectangles, that would give us the actual area. If we could somehow have, infinitely many rectangles. I know that doesn't make a lot of sense because how do you add up infinitely many areas, and you don't. But that's kind of the thing we're kind of going to strive for in 5.2. is looking at whether or not we can somehow find a way to make these rectangles obnoxiously small and make us have a ton of rectangles without actually having to fully calculate that many areas. But we're gonna stop there. We're a little bit early, but it's not worth moving on yet. So that's the end of 5.1. That's how 5.1 goes. It's pretty much all of these finding areas of rectangles, adding them together, calculating these Riemann sums. So you'll have homework on that next week. And remember, we have that kind of notation between n and delta t, where n is the number of rectangles and the delta is the width. If you have any questions, feel free to stick around for a little bit. Otherwise, have a great weekend, have a great spooky day, and I'll see you on Monday otherwise.